Hello, everyone, and welcome to another mini Sky Tonight. So I had a viewer ask me about the infamous dark matter and dark energy and what it is and how do we detect it, which is a very deep question. This is an area of constant research because hence the name dark matter and dark energy. They are dark and unable to be detected by normal means. And we're still trying to understand what it is, and we've discovered that they do indeed exist, but what we know about it is still ongoing research. So let's break down what these two things are, why they're different, and why they are such a source of constant research. As I sometimes like to say, they are the hot topic in astronomy. So our universe, when you think of our universe and everything in it, when you look up in the night sky, what is it that you come up with in terms of what's in our universe? So for many people, it's everything in our universe. We include planets, we include moons, we can include asteroids, we include comets, black holes, stars, galaxies, nebula. The list goes on and on. There are a ton of things in our universe. But what if I told you this is only just a small percentage of our universe as a whole? And this is only the stuff we can see. This 5% is what we call baryonic matter, or basically all the matter that creates stuff that we can detect. So when we talk about baryonic matter interacts with light very well. When atoms, kind of like in the Bohr model, receive energy, they release photons, which then those photons hit our eyes and we're able to see an image, kind of like what you see here on the screen. So all the stuff that you can list that's up in our universe in space is baryonic matter because we're able to detect it. We're able to see it with our own eyes. But what about stuff that doesn't produce photons? Even in the form of not only visible light, but infrared light or UV light, anything that can be detected. That is what is dark matter. Any type of matter that doesn't produce some kind of radiation that can be detected, whether it's through our own eyes, whether it's through different sensors, something of that nature that doesn't react to energy very easily. But yet it's not made of protons or neutrons, so it's not something that we're familiar with in terms of, because protons and neutrons do interact with energy, so it's made of something else. It doesn't produce radiation, but yet we detect it because it exerts some type of gravitational force. It has mass, and it's able to pull in with that mass to attract different objects. So how did we discover this idea of dark matter, that this wasn't just something written up on a chalkboard, but it was actually discovered? Well, we were looking at different galaxies and we were noticing motions of the stars in those galaxies, and we were able to calculate, okay, given the mass of this galaxy and the position of the star within the galaxy, whether it's closer to the center or further out towards the edge, we could get a rough idea of how fast those stars should go. And we did this within our own galaxy. Stars that were closer in towards the center of the galaxy should have higher radial velocities, versus stars that are further out are going to have slower radial velocities. So what we were predicting, like, it was this nice little bell curve to where as you were closer toward the center, it peaked, but as you went further out from the center of the galaxy, it trailed off. Since we're 2/3 of the way out, we were kind of predicted to be roughly a little slower than the stars that were closer towards the center of the galaxy. But that's not what we detected at all. In fact, many of the stars were not only faster, but about the same speed as some of the stars that were closer in on the galaxy. In order to have that kind of speed, you had to have enough mass pulling on these stars to be able to have them go as fast as they do. So that told us that there was some type of matter or mass within the galaxies themselves and around the galaxies that indicated that there's something pulling on these galaxies. Or even we've detected this with globular clusters going around center of galaxies, so hence the dark matter halo. Globular clusters are clusters of little stars, some of the oldest stars around our galaxy, and they orbit around our galaxy. And some of those speeds were just as fast as the stars within the center of our galaxy. So that told us that there was a lot of mass, 10 times more dark matter than regular matter within even our own galaxy and in other galaxies as well. And that the speeds were the same in all different directions once you got out a certain distance. And the only way that could happen is if there's a type of mass that is pulling in towards the center to keep the speeds going. So kind of give you a rough idea. So basically starting from the center of the galaxy and you go to a certain point, it reaches this peak. And we calculated that as you go further and further out, there's less gravitational pull from the center of the galaxy. So it's going to go a little slower. But that wasn't the case. We noticed even the stars further from the edge of our own galaxy were traveling just as fast as some of the stars closer in towards the center. So that meant that there's matter within between the galactic arms that basically said that it's being pulled. And galactic clusters and star clusters like globular clusters were orbiting at the same speeds as well. So this dark matter exerted throughout most of the galaxy. And we also noticed through dark matter that it created some types of a unique gravitational lensing that stretched, and some galaxies form in filaments, and as well as you have lensing that's farther out than where it should be, like in blank areas, and that the galaxies themselves kind of gravitationally pulled themselves in strands. And I'll show you a picture in just a minute. So talking about the gravitational lensing. So what is it? Basically, when you have a massive object in front of you and there's another massive object behind it, the light that's coming from the object behind is being bent around the galaxy. This was predicted by Einstein with his theory of general relativity, where space-time is bent and curved. So anything massive warps the fabric of space and time. So as light is traveling along the fabric of space and time, it follows along that curve. And so that's why you're seeing like this weird ring around a galaxy that's in the center. So that weird ring just happens to be a galaxy behind the center galaxy you see there. But it should be a perfect circle, shouldn't it? I mean, the galaxy we see in the center there's kind of perfectly circled, but if you look over here to the right, it's kind of nudged a little bit up to the right. So, but there's nothing there that indicates us that there should be any distortion or bending of some kind. So that was something weird. So that told astronomers that there's probably this extra mass going around the galaxy that's distorting the lensing just a tad more. And when you looked at a series of galaxies, we noticed lensing around a cluster of galaxies. And in order to be able to have this kind of lensing, you had to have a ton of mass. Especially when you see lensing that's just so random in random different places that doesn't look like it's even attached to different galaxies and or going even through some different galaxies. So that told them that these light streaks that were going through random galaxies that was stretched maybe was the artifacts of another type of mass. And maybe that mass was dark matter. And about the filaments. Now, the coloring that you see here is not what we detect because, again, remember, dark matter does not produce light. This is false colored imaging of those individual points of light that you see are some of the galaxies that we have detected. And we noticed that in galaxy clusters, they all kind of fall into these different lines and strands, kind of like filaments. I kind of like to think of this as like a neuron of some type, that with the outstretched other little filaments from the main neuron. And the galaxies themselves kind of detach in different ways, leaving blank spaces in between. So that told astronomers, in order to have galaxies that land in these kind of filaments rather than just spread out randomly, there had to be some type of mass or matter to attract them in these natural filaments. So what is dark matter made out of? So what could it be? We ultimately don't know. So hence the constant research that is being going on to understand what is dark matter. We do believe that it's part of what is known as the non-standard model of subatomic particles. Now, the standard model of subatomic particles includes all the different types of quarks: up, down, strange, charm, and top and bottom. So those are the different types of quarks that we know, and the different elements that we have in different types of matter are created from those subatomic particles. But what about other types of particles like leptons, like other types of Higgs bosons and things of that nature, like leptons and bosons and all those different types that are not the standard subatomic particles? What if they create different types of matter? And we have two different kind of categories for these quote unquote non-subatomic particles: machos, which are massive compact halo objects, and or WIMPs, weakly interacting massive particles. Like basically these are just either really heavy or just things that just don't interact with different things. They could be inert neutrinos or other types of exotic particles we have yet to discover. Hence the constant research. So we know that they could be different types of materials, but we don't know. And that hence why our constant discovery, because one of the hard features of dark matter is we see the results of dark matter, but we can't detect it itself. And that's the hard part. It's trying to look for something that you can't detect. So hence the constant research to find out other ways of being able to see the influences of dark matter to infer different things. Now, dark energy. As I told you, everything we see is 5%. Dark matter only is 27%. So what makes up the rest of the universe? About 68% of it is predicted to be dark energy. Basically energy that dissipates throughout the rest of the universe. So how did we discover dark energy? In 1998, the Hubble Space Telescope showed that the universe was not slowing down, because when we looked at our universe and we saw all these different galaxies, astronomers originally predicted that with them just being where they are and naturally slowly just drifting, just going on their own speed, not accelerating or decelerating, that sometimes they would get gravitational tugs from other galaxies that they would pass by. And they would slow down because they were being gravitationally pulled, and those galaxies would merge. And then more galaxies would merge and merge and merge, and then it would start to slowly slow down enough to where the gravitational pull between those merging galaxies would start to merge again, creating what is known as the Big Crunch. It's basically the opposite of the Big Bang, where the Big Bang is basically the explosion of creating our universe, that the gravity would gently pull it back to where it crunch again. But that's not what we were detecting, that the universe was not just flowing out at a steady rate, but indeed accelerating, going faster, as though it would go from one point and then just speed up away from that point over time. And astronomers were baffled by this, because it couldn't be dark matter, because matter creates gravity, and gravity is an attractive force. It should pull it in. And that's what they thought originally with the Big Crunch, that there's enough dark matter that the gravity from the dark matter would pull the galaxies back in. but that was not what we were seeing. But we were seeing something else. It was literally pulling the galaxies away further out and accelerating them. So hence dark energy. It was first predicted by Einstein. In fact, he called it his biggest mistake because he wanted to create it to where he created a universe where it was steady, it was stable, it was in a constant state. So he predicted that the universe had constant energy spread across it to keep it in this quote unquote stable state. But it turns out his quote unquote mistake may be a good explanation as to why we're seeing something being repelled out at a fast rate. That energy could be pushing the galaxies away at a faster rate and causing them to accelerate. And since it's evenly distributed throughout the universe, it causes it to spread out faster. So over time, we may have a galaxy and our galaxies so spread out that we can't see them anymore. And that this radiation can be spread out so far that it might thin out. We don't know. So hence, the constant research. In fact, to quote Einstein himself, if it wouldn't be called research if we knew what we were doing. Meaning that if we already knew the answers, if we know how to discover, if we already knew the answers, or we already knew how to find out the answers, it wouldn't be called research. We just discovered the answer. But in this particular case, we don't know. So something I always like to tell students sometimes, it's okay to not know. Because even some of the best experts don't know everything. And it's okay. That's what the great thing about science is it gives you the opportunity to find out. And that's what we're doing. We're trying to find out. So this is a kind of nice summary and an explanation of what dark matter and dark energy are and why they're two different things. So if you have any questions or comments, leave it down in the comments below. If there's a topic you would love for me to cover over, leave it down in the comments as well. And until next time, stay safe, stay healthy, and as always, never stop learning.